This is a short lesson on visually adding vectors. In physics, vector quantities are quantities where direction matters. Some examples are displacement, velocity, acceleration, force, and momentum. We can visually represent a vector by an arrow, like this one. The length of the arrow describes the property of the vector called the magnitude. The magnitude of displacement is the distance traveled, and for example, the magnitude of velocity is the speed. The direction part of the vector is represented by the direction that the arrow points. Now, something that's important to realize about vectors is that moving this vector around, changing its position, doesn't change the vector at all. I can put it any place I want, and as long as the length stays the same and the direction that it points stays the same, it's exactly the same vector. It's important to be clear that the arrow represents a vector. This arrow is not itself a vector. It's a stand-in to help us work with, compute, predict, understand things like displacement, velocity, acceleration, force, or momentum. Let me give you a scenario that will illustrate working with displacement vectors. Let's say that this morning I was good and I got up early and I went from my home to the gym to work out. I had a displacement, a change in my position from home to the gym. And I can represent that by creating this graphic where I have my home location or position, the gym position, and then an arrow pointing from home to the gym. That's my displacement. It has both a length, and that's the distance from the home to the gym, and a direction, which is the direction that I would need to travel to go from my home to the gym. Now, after working out, I felt like I had done such a good job getting up early and getting exercise that I deserved some donuts. And so I traveled from the gym to the donut shop. So now I have a second displacement. My initial position was the gym. My final position was the donut shop. And I have a displacement vector pointing from the gym to the donuts. The length is the distance between the gym and the donut shop, and the direction that the arrow points is the direction I would have to travel to go from the gym to the donut shop. Now, my overall beginning location was my home. That's where I woke up. That's where the whole story began. And then I have an overall ending position at the donut shop. And so by the time I reach the donut shop, ultimately I have traveled from home to the donut shop. And so I can look at my net displacement. My net displacement is from the very beginning to the very ending. And I've drawn it here with a different color arrow. What I've done is I've added up two journeys. One journey from home to the gym, and then I added to that a journey from the gym to the donut shop, and it's produced an overall or net or resultant journey from my home to the donut shop. For most people, this scenario is pretty straightforward and easy to understand, but we can abstract it a little bit to how to deal with adding together journeys or vectors in general, and let's take a look at that now. So I have here two arrows. They could be vectors. They could represent displacement or velocity or acceleration or force or momentum or even something else. What I want to do is add them together. This makes, in some ways, the most sense if we talk about displacement. So I can imagine that these represent two journeys, but taken immediately one after another. Initially, it looks strange because they're far apart from each other. There's a big distance here. But remember what we talked about earlier. I can move these vectors around, and it doesn't change the vector as long as the length and the direction stays the same. And so I can arrange them this way. What I have here now could represent displacements where I began at this location, traveled in this direction, this distance, perhaps stopped, and then began here and followed a path this direction, this distance to the end. Now, what's my net or overall displacement? Well, I began at the very beginning here, and I ended at the very end there. This orange arrow represents my net or overall displacement. And the arrangement of these vectors to determine that overall displacement has a particular name. We call it tip to tail. Now, it wasn't really clear from those two arrows sitting on the page which one was supposed to be first and which one was supposed to be second. But let's stop for a minute and think about addition. So if I have two things that I'm adding together, column A plus B equals C, you know that if we switch these around so that it's B plus A, those should still equal C. Those should still equal the same thing. And this rule holds true for vectors as well. Let's just check this. So this time, from my very initial beginning location, I'm going to start by going this way, and then the second part of my journey will be this one. And look, it does end up at the exact same location. So we've demonstrated that this is true for vectors as well as normal quantities. Talking about displacement is usually the most straightforward way to describe vectors because we can all imagine making journeys with multiple stops, running errands where we switch our direction. It's a little bit trickier when we start talking about quantities like velocity. So what does it mean to add velocity? Well, here's a scenario. Sally wants to cross a river in her canoe. The river flows westward at 3 meters per second. So this is a vector, this is a velocity vector. 3 meters per second is a speed, and then westward is the direction. So I could go ahead and draw that. On a normal map, north is up, and then west is to the left. And so I'm going to draw an arrow moving to the left. This represents the speed of the river. Now it says Sally paddles her canoe due north as fast as she can. She can travel through the water at 1.5 meters per second. We actually have a velocity here. We have a speed, 1.5 meters per second, and a direction, north. So what's happening is we can add Sally's velocity to the velocity of the river. So now we need an arrow pointing north, which will point upward in my coordinate system. And 1.5 meters per second, that's about half. Well, that is half of 3 meters per second. So the length should be half. And I'm going to estimate it. It's probably a little bit short. Let me see if I can stretch it out a bit. All right, there we go. So let's think about what this means. If we imagine that Sally is beginning her journey here, the river is going to carry her 3 meters to the west every second. But during that 1 second, she is also contributing motion that takes her 1.5 meters to the north. So these two arrows are not happening one after another. They're happening at the same time. And the results, her resulting motion through the river, is going to take her in this direction. So I've added the velocity contributed from the moving water and the velocity contributed by Sally's effort, and the result is a velocity vector that points northwest and is longer than either the river flow or her paddling by themselves. So her overall motion through the water, her overall velocity, is going to be represented by this orange vector. Finally, I'd like to show you how you can use graph paper to do visual vector addition in a more quantitative way. So I've drawn a coordinate system. It has velocity north, velocity west, east, and down here is south. On this graph paper background, one square represents 0.5 meters per second. So this blue arrow represents the river. And it is traveling at 3 meters per second, and so it covers 6 squares. 1, 2, 3, 4, 5, 6. That's the flow of the water. If Sally didn't paddle her canoe at all, that would be her velocity, but she contributes to that. And this dark red arrow represents Sally's contribution. It is pointed northward, and it has a length of 3 squares, which is 1.5 meters per second. Now I can put these together to produce the net overall resultant velocity. It's going to begin at the very beginning and end at the very end. And so to figure out the actual speed of this, I can visually count up the squares. I can perform something called Pythagorean theorem, where the length here, which is 3 meters per second, the length here, 1.5 meters per second, I combine them to find this hypotenuse of the triangle. The hypotenuse of the triangle will be equal to the square root of 3 meters per second squared plus 1.5 meters per second squared. And so the length of that resultant vector, the hypotenuse, the actual speed through the water, should be about 3.3 meters per second. That was assuming there are actually 2 sig figs on this 3 meters per second. And that concludes this short lesson.